And this is Bob, K5CRX for the McKinney Amateur Radio Club. This is session 2 of our general prep licensing class. We're prepping folks with the technical aspects of that exam to help them pass that exam. And we hope that you'll enjoy the session tonight and get something from it that will maybe explain a question or an issue that you might have with some of the technical aspects. Again, we're covering the technical aspects in these sessions, not necessarily the rules and regulations or the operating procedures, as we're anticipating. You'll read those on your own and prepare for those on your own. We also recommend any number of the great online ham prep tests that are out there. You go through those tests, do the practice questions. And generally, our advice is when you start getting about 90% consistently on taking the practice exams, it's time to go take the test and you'll be just fine passing the test. So with that, we'll be starting here in just a couple of minutes. I was telling Dan a little bit earlier there's a couple of email addresses for me. The K5CRX at ARRLnet is working now. When we were doing this last week, it had not been turned on yet, so it is working now. If you want to use any one of those, feel free by all means. Okay, we're just going to review a couple of the slides from last week first, and then we're going to go into oscillators and components and then circuits, which is talking a little bit more about some of the components, their interactions. There's some terms, there's a few formulas and other such things, which we'll talk about as we go along, and whether you really need to memorize those formulas or not. My personal preference and feeling, and for myself anyway, is I don't memorize the formulas. I memorize the answers. If you go through the practice test a few times, the answer will just pop out when you hit it, and you just know that 3.7 is the right answer or whatever it happens to be, and you just click it and go on. But if you want to know what's behind the formulas, of course, we try to give some of that information for that as well. I did also email this part out as well as the sessions we did last week, which included electrical principles. Email those out. Anybody else that wants that, by all means, email me here, and I will make sure that you get those that information as well. Okay, so let me change hands. Okay, so we're going to oscillators and components and circuits tonight. We'll see how that goes. If we have some extra time, we may jump back over and cover some of the electrical safety things that are kind of nice to cover. The receiver and the transmitter sections, I think, merit some discussion and some time, so that's why I listed those as separate sessions. By the way, you might also notice, as the way I have those paired up, that's only 5 groups. That 6th one is kind of in limbo just in case we need some extra time, or if not, we'll pick up another session and we'll fill it in. So we certainly won't lose anything within the 6 sessions. Okay, quick review on the metric system, and we will use this in these 2 sessions tonight. Remember the how things work there in groups of 1,000, the kilos and the megas, and then we go small, we go milli, micro, nano, and pico, back and forth. And we will see one question tonight where nano and pico are mixed in a question, and you have to watch out for that and make sure you catch it and convert both to the same. You generally convert the nanos to picos, and then you can just add everything up and it works great. But just watch out for that when you see that happen. And then this is as far as we're going to go on this particular slide pack. But to remind us of Ohm's law, E equals I times R and P equals I times E, or we call it ear and pi. If you have the E equals I times R, then with a little bit of algebra, you can derive the other two. I is equal to E over R, R is equal to E over I. And then the power formula, power is equal to current times voltage. Current is equal to power divided by voltage. Voltage is equal to current divided by power. Or if you have the other terms, you can use the squares there, E squared over R or I squared over R, depending on what terms you have. So as I said, I'm not going to dwell a whole lot on that one. Just want to do that quick reminders because those are key elements. So I'm going to stop the share. All right. And if you'll give me just a moment here to go back to my desktop, and I'll get the next one keyed up. Oh, come on. Come on, computer. Don't quit now. Okay, some things are easier said than done, aren't they? I'm learning some things you need to leave on the screen all the time instead of going back and forth. So bear with me, please. Okay, here we go. Oscillators and components. Go for it. and back to Zoom. And here we go. Share, share. How are we doing? Are we okay? Everybody see me okay? All righty. I'm going to do the same thing that I did last time. The Gordon West slides are set up with about half the slide deck going into a verbal description of all the questions, and then we actually go through the questions. So what I've actually done is I've copied a couple of these explanations and put them down next to the question that it relates to, so we can discuss the topic and then have the question right after that. And I think that will make more sense. So kind of blink your eyes. I'm going to try to go, and it's not going to let me do it. I have a problem with my little clicker not always wanting to do what I want it to do. Well, if the mouse will work, that's okay too. I don't care. Hang on, don't get dizzy. Okay, there, let's see, back one. Okay, that's where we're picking up. Now then, this is one of the ones that I copied down because there is a question about an oscillator. As it says at the bottom, an oscillator is an amplifier with positive feedback. And what this slide is attempting to show, this little symbol there, it normally represents an amplifier. And oftentimes it will represent an operational amplifier, as we call it, or an op amp, which is a special type of little integrated circuit that has a nice amplifier built into a nice composite little package. And what this is showing here is we're taking a sample of the output sine wave that's coming out and feeding it back to the input of the amplifier. That's kind of like getting feedback from a microphone. We've all seen that, where we get the microphone in front of the speaker and we get that terrible hum or squeal. That's called feedback. Basically, it's picking up the mic, running it through the amplifier, sending it back out again, coming back through the mic, and it's in an endless cycle at that point. That's what we're doing with an oscillator. We're basically just taking some of the output, feeding it back to the input, so that that continuous reverberation continues forever until we disconnect something. So that's kind of the idea behind it. This particular thing, they're showing a sine wave. We can use different components. We can have it generate a square wave if we wanted to, or a sawtooth wave, which is this up and down thing there. We can control the frequency with various components, all kinds of ways to do that. But the point here is that an oscillator is just an amplifier with a positive feedback. And again, as I said earlier, if you have any questions along the way, by all means, please stop me and say, hey, what about this? I got to move. Okay. And I'm sorry, I'm having a little problem getting my toolbar out of my way here. It just doesn't want to be where I want it. There we go. Which of the following are basic components of a sine wave oscillator, which we just talked about? What do you think? Anybody want to chance it? Which one has a feedback loop?
Is the frequency multiplier in a mixer?
No, we're not multiplying or anything. The key here is this feedback loop right there.
D.
Okay, the filter is that resistor that we were showing in that first diagram. The filter they're showing just as a resistor. Generally, that would be more complex than that. There would be a capacitor and maybe an inductor and a couple of other things in there to get a specific frequency out of it. But at any rate, the key there to it is it's a feedback loop. There's no such thing as a feed forward loop. That's something they just made up, and the other two are basically not really related. Is that okay? Are we clear on that? We can certainly talk about it if you want to. Okay. If I don't see a hand go up, or if you don't break in and say something, I'll keep going. Okay. What determines the frequency of an LC oscillator? You remember what L represents an inductor, C represents a capacitor, L is measured in henries, capacitance is measured in farads. So when we put a capacitor and an inductor together, we can use that to control the frequency of an oscillator. So out of those things, the number of stages has nothing to do with it. The time delay of a lag circuit is something somebody made up, which leaves us with inductance and capacitance in the tank circuit. Now, the reason I put this little diagram down at the bottom there, that's what we call a tank circuit. The reason it's called a tank is we apply power and stick a signal into this thing. The inductor charges up slower than the capacitor does. Capacitor charges up. It just starts to discharge back through the coil. The coil charges up as the capacitor discharges. Then the coil discharges back into the capacitor. Capacitor discharges back into the coil, and it goes back and forth to create the tank circuit, or the portion that makes the oscillator oscillate. So if you see that like that, you'll kind of know what that is. That's called a tank circuit. Okay, inductance and capacitance in the tank circuit. And we have two questions on vacuum tubes. And as they made in the comments of this, yes, there are people that still use vacuum tubes. A lot of the amplifiers that we use these days are still vacuum tube powered, because you can get so much more power out of those fairly easily, as compared, and less expensively actually, than using solid state components. To get 1,500 watts out of solid state components, it takes some really high power, expensive transistors to make that happen. So a lot of tubes are still there. Okay. This particular tube diagram that we're looking at here is a 5-element tube. You have the plate on top, a screen grid right under that, a control grid under that, and then the cathode under that. The cathode emits electrons. The plate is positive, so it attracts those electrons to go through to the plate. And in order to control the flow of electrons, we can put a negative voltage on this control grid, and it will slow down the flow of electrons. That's the whole idea behind it. So in the question, you notice it says, what regulates the flow? Consider the control grid as one that regulates, if that'll help you remember it. Regulates and controls is the same thing. So the control grid is going to control the flow of electrons across the tube from cathode to anode, or from the cathode to the plate. All righty. So it's the control grid. The screen grid, which we're not talked about, but which we're now going to, has a whole other purpose. The screen grid is biased totally different. Its spacing is critical within the tube itself, and it's placed such that it reduces this capacitance that exists between the control grid and the plate. Without that, the tube is limited to fairly low frequencies. But by putting this a little bit of bias in there on that, we can actually neutralize, as it were, that stray capacitance. So we're using that screen grid to reduce the grid to plate capacitance. Okay? Good. All right. What are the operating points for a bipolar transistor used as a switch? Well, first of all, we can have a transistor, and its most common application perhaps is as an amplifier, which means its output is varying up and down all the time. But it can also act as a switch where it's either totally turned on or it's totally turned off. If it's turned on, it is cut off. If it's turned on and fully conducting, then it's called saturated. And that's what this little chart down here in the lower right is trying to show. The cutoff region up here is a region where the base of the voltage over here applied to this base is such that the transistor acts just like this switch right here. That switch is open, then the transistor is in the cutoff region. It is cut off. It's turned off. Then we have an amplifying region, which is this region right in here. We're not going to use that as a switch. We don't want it to amplify. We either want it on or off. And when we bring up the base bias to the right place, it will turn off the transistor, and then it will be in its cutoff region. And we look at this little diagram, which is kind of cute over here. This is the touch switch of an LED and a transistor powered by a battery. And when you put your finger between those two touch points, it allows a positive voltage from the battery through the resistor to the base of the transistor. That's a fairly high positive voltage, and it will compared to what might be if we divided it or we used some extra resistors or whatever. Anyway, it's positive enough. It'll cause the transistor to turn completely on, act like an on switch right there, and that will, of course, turn on the LED. When you remove your finger, the voltage goes away, the transistor cuts back off. It has nothing on the base to turn it on, and it turns itself off. So the transistor is going to operate as a switch when it's in its cutoff and saturation regions. Okay? If I go too fast, tell me. What's the characteristic of a low voltage ceramic capacitor? I thought one picture's worth 1,000 words. Over here on the three are three different flavors of ceramic capacitors, and then a little diagram of what it really is. It's basically just a little piece of material between two conductors encapsulated in some kind of plastic or ceramic material to insulate it. The good part about this is it's cheaper than dirt. You can generally buy these little capacitors like that guy there for 2 or 3 cents a piece. They're very, very inexpensive, but they're very solid. They don't tend to drift really bad, and they're very long life, low maintenance. They just work. So they're a great little capacitor to use in high volume. So the big advantage for that one, probably I gave it away, didn't it? It's a low cost. It's cheap. Which of the following describes the MOSFET construction? Anybody know what MOSFET stands for? Just for grins? Metal oxide semiconductor field effect transistor, which is a little different from a junction FET or junction transistor, but we don't worry about that one too much. What following describes it, and they have a picture of it down at the bottom there. The gate is like the base on a regular transistor. We put a voltage on that gate, and it causes the conductor to causes the transistor to conduct or amplify back and forth, whatever it is it's hooked up like it's supposed to do. So to make this thing work, we have a piece of conducting material here. And before we get to the gate connection, there's a real thin little film insulator that's put right across there. And then this gate comes in on top of that with another little element so that it's actually working magnetically more than anything else. So there's a thin insulating layer between the gate and the rest of the conducting part of the transistor. So that means B is going to be the answer. It's separated from the channel by a thin insulating layer, which lies right in there. Okay, diodes a little bit. 2 types of diodes on the test. The germanium diode, which was your old original diode that we started out with in the crystal radio days. It was, in fact, a diode. It has a very low forward turn-on voltage, which was the reason we could use it as a detector in a little no amplifier radio, no crystal radio. You can't use a silicon diode in a crystal radio because the forward voltage is too high. It'll never turn on. But the signal that we get off the antenna through the coil, capacitor, whatever we use with a crystal radio, is enough that we can actually turn this diode on and make it work. This is a picture of one. This is generally what you'll see with the germaniums. If you look right there, there's a little cat whisker right there pointing to a piece of material inside that glass bead. And that was literally what we did with your original germanium diodes. We had a little chunk of germanium in what we called a cat whisker, which was a spring-loaded wire. And we would move that wire around, find a sensitive place on that crystal, and then that would allow our radio to work. Well, on these guys, we put it encapsulated in glass so it stays in one place and it just works. However, they are very low voltage devices. They're normally very low frequency devices. The key to this one, though, is the forward voltage to turn it on is 0.3 volts, 0.3 of a volt. And this is the symbol for it. The symbol is the same whether it's silicon or germanium, but that's the symbol for a diode. Current flows through from the cathode to the anode here, and as I'm looking at this, from the right to the left. So when we're playing with our crystal radio, there's enough signal hitting in there to exceed 0.3 of a volt so that the crystal diode can work or detect the signal that's coming in. That's a whole other discussion we won't go into right now. That's the germanium diode. Conversely, the silicon diode looks generally like that. You notice this has a lot heavier encapsulation. These little diodes come in higher voltages, higher amperages, you name it. That one looks like it's a 1N4007, because you can see the 07. The 1N4000 series diodes, 4007 is a 1,000-volt peak diode. 1N4000 is a 50-volt diode, and they conduct 1 amp. So they're heavy-duty diodes by compared to the germanium, but they do have a much higher forward voltage, which is 0.7 of a volt. Germanium 0.3, silicon 0.7. A shift register. That sounds like some bum on the street, doesn't it? Well, maybe not. And don't forget to drink your Dr. Pepper. Okay, what is a shift register? And this is a shift register down at the bottom. We've not talked about flip-flops and digital components to speak of. A flip-flop is an electronic circuit that you put a signal into, and it will hold a particular state, like a 1 or a 0, until you change it by some means. So we're showing here 4 flip-flops. We're putting a signal in on the data input, and that signal sits there, rests on that data input, be either a high or a low in digital logic. And then we come in with a clock signal right there. And when the clock signal hits it, it tells this output over here, emulate whatever that input was. So if it's a 1, it switches this to a 1. And then it sits there. Then this 1 is now sitting on this flip-flop. The next clock cycle, that 1 gets transferred across. Next clock cycle, it goes to the next one. Next clock cycle, it disappears or goes to the output. So it's called a shift register because it's shifting a bit from one flip-flop to the other based on the clock input down at the bottom. So the answer turns out to be, whoops, wrong button, a clocked array of circuits that passes data in steps along the array. The circuits are flip-flops. Not that that matters, but that's how it works.
Questions? On the ham study deal, they give hints, and a good way to remember it is you clock in for your shift.
Good idea. I hadn't thought about that. That's a fabulous idea. Yes, clock in for your shift. Clock the clock array that shifts things along the way, passes things along the way. Good idea. Thanks, Jeffrey. Anybody else? Okay, moving right along. How is an LED biased when emitting light? We haven't defined the word bias. Bias is merely an applied voltage that makes a semiconductor do something. It can be a base bias on a transistor, a voltage we apply to the base of a transistor that turns it on or turns it off or puts it in its amplifying region. Or in this case, an LED, a light emitting diode. We bias it on. We put a voltage across it that will conduct through it, and that will turn it on and make it emit light. So how is it biased? It's biased forward like all diodes, so it has to flow right through the cathode, through the anode, and when it does that, then the diode will emit its light. I keep wanting to press the right mouse button instead of the left one, so it has to be forward biased. The LEDs are always indicated by those 2 little arrows. Sometimes it's just a jagged arrow that comes out, but there'll be an arrow there indicating that it's emitting light. How does a liquid crystal display compared to an LED display? Well, you might remember that liquid crystal displays are usually like this, that you don't see the digits necessarily or the dots. We'll see those in our watches most often, versus an LED display where you can sometimes actually see the LED segments. And these are called a 7-segment LED display. We apply a voltage between a common and one of those segments along. Each one of those is a diode, an LED diode. We apply voltage across it, it turns it on, and we can see it. Whereas on the liquid crystal display, it doesn't need that much power to turn on an LED. It uses much, much, much less power. It's more of an electromagnetic field that lights up a spot on the display itself. Now, another great thing about these guys, they work better in high light situations. If you have an LED display and there's a lot of light, you can't see it. The light overpowers it. On the other hand, the LCD, liquid crystal displays, usually work better because they're using contrast to display their pattern, and more light makes it more visible. So how does a liquid crystal display compare to an LED? Of the choices that are there, the high contrast and ambient lighting, and I keep pushing that wrong button, makes it work better where there's lots of light, plain and simple. What is an MMIC? MMIC. And I don't know any way to say this, but just say what it is. It's a monolithic microwave integrated circuit. Could look something like the little diagram that's there at the bottom. It's just a little integrated circuit that is so designed that it can deal with microwave frequencies. If you've dealt with microwave at all, you know microwave is very squirrely. Just crazy things can mess up microwave. Short distances between components, any little loop just a loop in a wire, if a little wire looped around like that would be seen as an inductor at microwave frequencies. It would look like a coil. So it's microwave is very squirrely, is the way I like to say it. But a MMIC monolithic microwave integrated circuit. Fortunately, that answer is the only one with the word microwave in it, isn't it? So that should help. What kind of a device is an integrated circuit op-amp or operational amplifier? I mentioned that at the very beginning. And here are some more practical diagrams of op-amps. You notice there's a plus and a minus input on these op-amps. If we come into the plus input, we don't invert the output, i.e. when this input goes high, the output goes high. Usually, however, we go into the minus side, the input goes high on the input, the output goes negative on the output, called inverting. At any rate, these guys are analog devices. They don't turn on, turn off. We don't use them as switches. We always use them as amplifiers, amplifying then, implying that the voltage level is always changing, which means it has to be analog, because digital is 1 and 0, on and off, positive, negative. So analog is going to be the right answer for those guys. An op-amp is an analog device. Those formulas at the bottom, I don't think are particularly significant, but if you're interested, they're there. You can use those formulas to calculate the gain of an op-amp. You use the reference resistor, the feedback resistor, and the input resistor. The ratio of those guys determines the gain of an op-amp. Okay. Which of the following is an advantage of a CMOS integrated circuit compared to a TTL integrated circuit? We're back to terms again. CMOS, you remember we mentioned that already, is a complementary metal oxide semiconductor. It's using metal oxides, very thin layers of material, versus transistor logic, or TTL, which is made with transistors inside an integrated circuit where one transistor is hooked to the next one directly, or through a resistor sometimes, but often directly, or through a diode, back and forth. So we have transistors talking to transistors in TTL. Metal oxide does the same thing, but it does it with a different process that takes a whole lot less power. The TTLs were the original ICs that we had in the digital world, but they were very, very power hungry. And the CMOS circuits came on the scene. They used about 1/100th of the power of the TTL. They were very, very efficient. They were very, very picky, though. You had to be very careful with them because static could wipe them out. They've improved a lot since then, but that was the original. So which of the following is an advantage of CMOS? The main advantage is the power consumption. Use much, much less power than TTL. It's all transistors and diodes. Which of the following describes the function of a 2-input AND gate? And we're getting into a little bit of digital world here at this point. I drew a little diagram at the bottom. I've got to move this thing just a second where I can see that. The AND gate, by its very name, says if A is high and B is high. Now, a high would normally be plus 5 volts in most cases. So if A is as high or 5 volts, B is high 5 volts, then output C will likewise be high 5 volts. A and B equal C. If either of these is low or ground, then C will also be ground. That is, it will not be turned on. And we use a truth table, we call it, to illustrate that. So, and they're using X and Y in the table instead of A, B, and C, but it works the same. So if A and B are low, the output is low. If either one is high, but one is still low, the output is still low. The only way to get a high is to have 2 highs coming in. That's the nature of an AND gate. If you get a chance to take the digital class that we do sometimes, we go into that quite a bit, and we actually play with some of those just a little bit. So which is going to describe it? Essentially, we're saying that we have to have 2 highs in to get a high out. Output is high only when both inputs are high. Would you buy that? So far, so good? Clear as muddy water on a windy day. Okay, moving right along. One more. Still a little bit of digital stuff here. How many states does a 3-bit binary counter have? Binary means ones and zeros, counting in ones and zeros, or highs and lows. 3 bits means we have 3 different transistors or 3 different devices, each of which represents one of those 3 bits. And I've labeled the bits here A, B, and C. So we have 3 bits. If all 3 bits are 0, that would have a value of 0. If you want to convert it to numeric values, it would have a value of 0. If we have a 0, 0, 1, 1 represents the digit 1 there, so that would have an actual value of decimal 1. The values go 1, 2, and 4. The powers of 2, basically. And then you'll notice we're just flipping these bits back and forth and going from right to left. So this would be a value of 2. Value of 2 plus 1 is 3. Value of 4, 2 squared. And a value of 4 plus 1, 5. A value of 4 plus 2, 6. And all 3, 4 plus 2 plus 1 being 7. So we count those up. How many states can it have? 1, 2, 3, 4, 5, 6, 7, 8. Because all zeros is one of those states. So the answer for that has to be 8. A 3-bit counter can have a maximum of 8 states. So far, so good? Okay. Okay, and that is the end of that one. So let me open a different one. And let's see, we want to go to circuits. And go full screen. And again, I'm going to zip through this till we get down to the questions. There's I think there's 89 slides in this particular one. I believe that's right. All right, back one. Okay, yep, there we go. Here we go. Circuits. Before we go into circuits, this is a reminder slide from last week. You'll see the tank circuit we talked about earlier over on the left. X sub L is inductive reactance. X sub C is capacitive reactance. It's both called reactance. It's resistance to the flow of AC, measured in ohms. However, an inductor and a capacitor essentially operate backward from each other. Just about anything one does, the other does in the opposite direction. And we'll see that coming to pass later on. Formulas for these things, if you want to figure out resonance for these things, we'd use this X sub L and X sub C. I don't think there's any place where we actually have to use that, but it's kind of nice to know that you can get that formula if you ever need it. Now then, let's get serious. And I've got to minimize that so I can see the screen a little bit better. Oh my, I think this is one of those places where it would be nice to have 2 monitors, I suppose. Okay, this particular diagram that you see down on the right, and by the way, I have you minimized so I can't see you. So if you need to tell me something, you'll have to tell me audibly so I can hear you, as I can't see you. We have a little circuit here, which is a Hartley oscillator, which they fortunately tell us right there. We know it's a Hartley because it's using a tap coil. That's characteristic of one of the types of oscillators. That particular part is not on the test, by the way. They're going to ask you to identify the different symbols on the test. They do not ask you to tell the function of the particular component. They just want you to know, what is it? So here we go. Let's look at these things and see if we can figure out what they are. Number 1, right in the middle. Everybody remember that one is an FET, field effect transistor. Number 2 is a regular transistor, regular junction transistor. Number 3 is a regular diode, just a plain old diode. Number 4, though, is a weirdo. Number 4 is a varactor diode. A varactor diode characteristic is that its capacitance changes as the voltage across it changes. So just for grins, on this particular circuit, you'll notice there's a potentiometer there with a sliding arm that's hooked up to your positive input and the ground on the other end. So as I move this slider up or down, I can increase or decrease the voltage across that varactor diode, which will cause its capacitance to increase or decrease. That capacitance, essentially in series with this little tap coil down here, creates a type of tank circuit. And then by changing the capacitance, I can change the output frequency of this oscillator. That's what that's all about. So that's called a varactor diode, V-A-R-A-C-T-O-R, varactor diode. Number 5, the little squirrely bent ends on that indicate that's a Zener diode. A Zener diode's function is to provide a stable voltage. And since this voltage at this point for the varactor needs to be very stable, we're using that Zener diode to give it whatever voltage it operates at. And that will give us a very stable voltage over there. Number 5. Number 6 is a transformer. It's a 2-winding transformer. Notice there's a metal core. Those little lines in between indicate a metal core. 2 windings, a primary and a secondary. So it's a transformer. It's an output transformer in this case. Number 7. And when you're looking for it, that's a whole other thing. 7, there it is. The tap coil. Sorry. And there are a couple of questions on there you have to be careful about. It mentions the tap coil in one of the questions, and it mentions 2 windings in the other question. So number 6 is the 2-winding transformer question. Number 7 is the tapped inductor question. That means that there's a coil of wire that somewhere down in the middle of that coil, there's a tap put onto there. Basically, this gives a feedback loop that makes the oscillator continue to oscillate. But at any rate, it's tapped down in the windings of the coil. And number 8 is a bypass capacitor. We said that we're getting a solid voltage off of this Zener here. So we put this capacitor there essentially to make sure that it keeps that voltage stable and solid. It doesn't have a chance to vary by up and down. 8, excuse me again. Number 9, another resistor. Just a resistor taking this transistor to ground. It's just a resistor, nothing special about it. Number 10 is a bypass capacitor. It's allowing the signal that's generated off these 2 items, this oscillating signal, it allows the signal to pass through the capacitor, but a capacitor does not allow DC to pass through, because you'll remember we've got DC coming through here, going down here. We don't want that DC going into our field effect transistor. So 10 is a blocking capacitor to block the DC. And we do have an 11 is a potentiometer or a variable resistor, if you want to call it that. You call it either one, both are correct. A variable resistor is also called a potentiometer. So that's the circuit we're going to look for. Now we're going to practice it. Okay, and there my little control bar keeps getting in the way of what I need to see here. Let me see if I can find a place to put it. That'll work. Which figure represents the FET? Number 1, right? Which is symbol 1 there, item C. Okay, next question. Which represents the Zener diode? That'll be item number 5 right there. So it's going to be D, symbol 5. So again, we're just basically reviewing what we've already covered. The NPN junction transistor, the regular transistor, is this little guy here, number 2. So that's going to be B. And then this is where we got to watch it. The multiple winding transformer. Multiple windings means 2 or more windings, which number 6 qualifies as. This is a single winding with a tap. So we have one winding, another winding with a core in between. So it's going to be item number 6. Which figure represents a tapped inductor? That's number 7. That's the little tap that's coming off the side there. Just a coil of wire with a tap on it to attach to some one of those turns of wire in that thing. So that's going to be number 7A. Answer A. And we're through with that. Any questions or thoughts about that before we go on?
Go back if you can.
Oops.
If you can't, that's fine.
I just messed up. I got to get back to my screen share just a second. I messed up.
I'm sorry.
Nope, that didn't do it.
Just thinking
there
on
we
the
go.
transformer.
Okay, I'm sorry. Now back up. You said.
Yeah, if you can, 1 page.
How
So
far?
number 6, the transformer. When you
Yes.
build your end-fed half-wave antenna, you'll build one of those.
That's correct. Yes, we do. Yes, we do. Instead of using metal plates, we usually use a toroid transformer. But yes, it's the same idea. Good observation. Okay, let's go on from there. How does the total current relate to the individual currents in a parallel? Can you see my screen, by the way?
Yes.
Yes. Okay. When I switched back and forth there, I lost the control panel for Zoom, so I'm going to leave it like this. How does the total current relate to the individual currents of a parallel circuit? So I picked this up someplace, just a little parallel circuit with the values we're not worried about. Got current flows from negative to positive, so we've got current flowing through there through the first resistor back to plus, current through the second resistor back to plus, current through the third resistor and back. They're different values of resistors, so they're going to have different amounts of current flowing. And the question is asking then, what's the relationship of all these currents that go through there? Are they independent of each other? Do they all sum up, add together, or whatever? And the idea actually is that they will sum up. So if this has 2 milliamps, this has 4 milliamps, this has 6 milliamps, I'm just pulling numbers out of the hat. We would just add those numbers up, and that would give us the total current dissipation of all three of those resistors. So what's our answer going to be? The sum of the currents through each branch, and they consider each resistor as being a branch when we have a parallel circuit. It wouldn't matter if there were another 10 resistors out there, that idea would still work the same. We would just sum up the currents through each one of those resistive branches. Why is the primary winding of a voltage step-up transformer usually larger size than the secondary winding? Okay, if you think back to that picture of the transformer, as Jerry pointed out, normally we put our input signal or voltage or whatever it is on the primary and take the output from the secondary. That's normally what we do. However, we can work it backward too, which we'll see in another question. The primary side normally would be the controlling side. For example, if we were using a household voltage and current, we put 110 volts in on the primary winding. And then on the secondary winding, we would see a voltage come out of that. And the amount of voltage will be determined by the number of windings on the transformer. Interestingly enough, there's a crazy thing that happens with transformers. We can step the voltage up or we can step the voltage down. When we do that, conversely, we also step the current up or down in the opposite direction. So if I have a step-up transformer, that normally implies I'm going to put 110 volts in, I'm going to get, say, 220 volts out. Say it's a 2-to-1 transformer. It's going to be a step-up 2-to-1. I put 110 in, I'm going to get 220 out. And if I have 1 amp flowing in the primary, though, I will only have a half amp flowing in the secondary. Again, the current goes in the opposite direction. Now, if I needed more current and less voltage, I could go the opposite way and do a 1-to-2 ratio, and then my voltage would be less, but the current would be double. I'd have a lot more current. So it goes back and forth. They're inversely proportional to each other. We generally consider the input or the primary winding as the one that we base everything upon. So this question then, why is the primary winding wire, the step up, usually larger than the secondary? Well, step up implies that we're going to have a lot of voltage and current flowing through it, because the secondary is going to have less current flowing through it, but more voltage. So I need a larger wire in the primary. Makes sense? So we're going to put the larger wire in the primary so that it can handle the higher current that the primary is handling. The secondary will have lower current if we are doing step up, as we said. Okay. Again, if there's a question, or if you want me to back up or slow down, or we'll talk about it some more, please tell me, and we'll sure back up.
No, I do.
I'm sorry?
You know I will.
Okay, that's what I want. Please do. What is the total resistance of 10, 20, and 50 ohm resistors connected in parallel? Well, I just borrowed that same drawing from before, even though the values are wrong. One of the clues on doing resistors in parallel, see the note there? The value will always be less than the smallest resistor. So we got 10, 20, and 50. We know this answer is going to be less than 10. We only got two answers that are less than 10, but which one is it? Okay, then we have to use our little crazy little formula. 1 over R1 plus 1 over R2 plus 1 over R3, which is 1 divided by 1/10 plus 1/20th with 1/30th. We add those two together, 0.1, 0.05, 0.2, 0.17. 1 divided by that is 5.88, which closest thing to that is the 5.9. And you'll find on these questions, if you do the math on the calculator, oftentimes you'll be looking for the closest answer. It won't be the exact answer. Some will be exact, but most won't. Okay, so we have to use the formula on that one since they're not of equal value. Now, there's another question coming up, so we'll prep you for that one. What if all three of these resistors were the same value? Say they were all 100 ohm resistors. Then what would the resistance be? Well, we know it's going to be less than 100 ohms, but since the three are all the same, we can just divide the value by 3, 100 divided by 3, and the resistive value would be 33.3 ohms. So when you have three in parallel that are the same value, it's very simple. But in this case, they were 10, 20, and 50 ohms. Okay, so we came at 5.88, which is close enough to 5.9. What's the approximate resistance of 100 and 200 ohm resistor in parallel? Now we got two in parallel, but they're not equal. So we know, first of all, that the resistance is going to be less than 100. So that gives us 75 and 67. It's got to be one of those. So this time we're using our little formula again. R1 times, this is just for two resistors. R1 times R2 divided by R1 plus R2. R1 times R2 is 100 times 200, the values, divided by 100 plus 200, those values, and then divide that out. Comes out to 66.67, which is close enough to 67 ohms, which is the answer. I think I mentioned this earlier. If I didn't, I'll mention it now. And if I did, it bears repeating. In most cases, it works perfectly fine just to memorize those answers. And as soon as you sit down in front of the test and you see that question, your eye just automatically flocks to answer D. You know it's 67 ohms. You don't have to do the calculations. Fortunately, there's not that many calculations, so but the memorizing them is not that tough if you want to take that tax. It's nice, though, I think, to know why we do that. So that's another reason for doing these classes. Okay, we're changing horses. Been talking resistors. Now we're going to talk capacitors. The equivalent capacitance of two 5 nanofarad capacitors and one 750 picofarad capacitors connected in parallel. Okay, capacitors and resistors work opposite of each other. Resistors in series, we just add them up. Capacitors in series don't work that way. Capacitors in parallel add up. And if you think about how our capacitor is made, that makes sense. A capacitor is made of two plates with an insulator in between. And if we parallel it with another two plates with something in between, they just add up on their capacitances. So it makes it simple. So really all we've got to do is add these guys up. The problem here is, though, we got 5 nanos and 750 picos. So how about if we convert everything to picofarads? 1 nanofarad is equal to 1 picofarad, playing with the decimals a little. So 5 times 1,000 would be 5,000 picofarads, gives us 5,000 plus 5,000 plus the 750, gives us 10,750 picofarads. But unfortunately, the answer is given in nanofarads. So we move the decimal places over 3 places to the left, and we get 10.75 nanofarads, which is the actual answer. We okay? Moving right along. I'm going to kind of keep it moving here, so we've still got quite a few questions to go, so we can try to finish on time. Capacitance of 3 microfarad capacitors connected in series. In this case, they're all the same value. We can divide by 3. So 100 divided by 3 was going to be 33.3, as we can see when we divide it out. Easy enough. Capacitance of a 20 microfarad in series with a 50. Now we're in series. We got to watch out for this. Like resistors, We've got to do the 2 this way. C1 times C2 over C1 plus C2. So we do the math on that. We come out at 14.28, which is closest to the 14.3. Keep hitting the right button. Sorry. Which of the following components should be added to a capacitor to increase the capacitance? Now, from a purely practical standpoint, think about this. If I want more capacitance, I need more plates and insulators. So if I put another capacitor in parallel with an existing one, that would add plates to it, which means the answer then comes out to just parallel it with another capacitor, and the 2 will add together. Which of the following components would be added to an inductor to increase the inductance? We have an inductor. We want to make it greater. We just add another inductor in series. Inductors act like resistors in that sense. They're calculated the same way as resistors. Capacitors are the odd man out. So in this case, we just add another inductor in series with it, and they will add together. Inductance of a 10 millihenry inductor connected in 3 connected in parallels. Well, remember, with 3 resistors connected in parallel, we just divide by 3. We do the same thing here. 10 divided by 3 gives us 3.3 millihenries, which is answer C. Just remember, capacitors are odd man out. Inductors and resistors use basically the same formulas with different letters. What is the inductance of a circuit with a 20 millihenry inductor in series with a 50 millihenry? They act like resistors. Remember, we just add them up. 20 plus 50 gives us 70 millihenries. Of course, the formula is there if you want it. What happens when an inductor is operated above its self-resonant frequency? Okay, what that's saying is, if I keep raising a frequency across an inductor, I can hit a point at which, once it passes its resonance, once it's done all it can do, basically, it becomes capacitive. And the reason for that is the coils of the wire no longer are able to charge and discharge with the inductance, but instead the turns between the coils on the inductor pick up capacitance, and it acts like a capacitor instead of an inductor. So there, of course, if you're engineering, you calculate all those things so it doesn't happen. But the idea is that when you pass it, the self-resonant frequency, it becomes capacitive. It acts more like a capacitor than an inductor. Reactance. Reactance is the opposition to the flow of alternating current. It's caused by capacitance or inductance, and resistance can be added in that as well if there's resistance as well. But the answer they're looking for here is capacitance and inductance. What occurs in an LC, an inductor capacitor circuit, at resonance? Resonance means that X sub L equals X sub C. The inductive reactance is equal to the capacitive reactance. When that happens, they cancel each other out. You remember that inductors and capacitors are opposite each other. So if I have a +1 on one and a -1 on the other, they, just like in algebra, would cancel each other out. So if I had current flowing through this tank circuit at resonance, then there's basically 0 resistance going through that circuit. The only resistance that would be there would be whatever residual resistance is there by the fact that this is a coil of wire, be some very minuscule resistance. In real life, you generally see a resistor up here someplace to limit current. But the idea is at resonance, the reactances cancel each other out. That's important, by the way. We use that in tuning circuits. We tune a circuit to its reactive point, to its resonant point, and at its resonant point, it will let that frequency pass right on through, so we can use that for tuning. Quite common. What happens when inductive and capacitive reactance are equal in a series LC circuit? We've already talked about that pretty much. Resonance causes impedance to be very low. If we're at reactance, that means there's no resistance from those two circuits. So whatever resistance is left, it's going to be very, very low. Whatever the residual components have in the way of resistance is all that's left. So the resonance causes the impedance to be very, very low. What is the opposition to the flow of AC in an inductor? It's called reactance. And this is just memorizing terms. Unit of measure is the ohm, fortunately. Which of the following causes opposition to the flow of alternating current in a capacitor? The reactance. How does an inductor react to AC? Okay, as the frequency goes up across an inductor, the inductor will tend to resist it even more, which means its reactance will increase. Frequency goes up, reactance goes up to that point we talked about before where it becomes capacitive. A capacitor, however, will do just the opposite. As the frequency increases, the reactance will decrease. Okay. And the letter used to represent reactance is the letter X. Whether it's X sub L or X sub C. Reactance is represented by X. When you put the X sub L and the X sub C along with resistance R, then it becomes Z impedance. Okay, a little bit of explanation of this next question, because it's a little bit of a hokey question, I think. The term impedance means the ratio of voltage to current in an AC circuit. Now, we could get into some deep analysis and illustrate that, but it's probably not worth it for this, for one question anyway. So remember, that answer is going to be the ratio of voltage to current. And the question is, what's impedance? The ratio of voltage, I got to watch it, voltage to current. Be sure you get the right one. Don't get the other one. Inverse of impedance? Well, if impedance is slowing things down, if we admit something, let it go through, we would call it admittance. And it's just playing terms once again. Fortunately, we don't go into that real deep with a lot of terminology. You don't have to dig into that very much. Which of the following devices can be used for impedance matching at RF or radio frequencies? A transformer, that's what Jerry mentioned a while ago. If you build an end-fed, you will build a transformer that matches the impedance of your feed line to your antenna. A pi network, which is a network using capacitors and inductors. A length of transmission line, if it's cut to just the exact length, can be used for matching. The pi network, by its tuning, can be used for matching. So the answer is going to be all of the above. Those all work for matching. What is the frequency above which a low-pass filter's output power is less than half the input power? Now, we're talking about filters here. A low-pass filter is one that's going to pass frequencies below a certain frequency. A high-pass filter would pass frequencies above a certain point. So here we're talking about what is the frequency above which the low-pass filter says you can't do that anymore. It's called its cutoff point. Basically, it's 50%. We go up to when we lose about 50%, we say that frequency has cut off. It's the cutoff frequency. What term specifies a filter's maximum ability to reject signals outside of its path band? This is an easy one. Reject signals, ultimate rejection. We're not talking about lovers here. We're talking about signals. The bandwidth of a passband filter is measured between what two frequencies? Now, band pass filter is a combination of a low pass and a high pass together. That's going to allow only a certain band or a certain bandwidth to pass through that filter. And if you look at the little diagram there, see that 3 dB? 3 dB is the half power point. So as the frequency goes up and we get to the half power point, then we start to conduct, and we continue to conduct until we get to the next 3 dB point, when the high pass filter cuts off and it shuts it off. So as we're looking at this, we're cutting it off and back and forth. Upper and lower half power points, the 3 dB point is the key to that, really. And I don't know an easy way to say that other than minus 3B is considered the half power points. When we get half the power going through, it's considered turned on. Half the power stops, we're considered turned off. The upper and lower half power points define the pass band. Circuits. Insertion loss is the key word that's out of that. And since we're running short on time, I'll email this to you if you want it, and you can read that a little bit later. What term specifies the filter's attenuation inside its pass band? The insertion loss. How much does it create a loss as the signal goes through? Wire round resistors are not to be used in RF circuits because the turns of wire in there become inductors. That's the ultimate reason behind it. Resistors inductance can make the circuit performance unpredictable, and that's very true. The wire wound resistor is a coil of wire. What advantage of a ferrite core toroidal conductor, which you were using as a transformer? The toroidal core can be made up of a whole lot of different kinds of materials. You get a type 43 and a type 23 and a type 66. And they all have different properties to pass different bands and do different things. So the answer to that is all of the above. You get large values from it. You can change the properties of it by changing the mix of the material. And most of the magnetic field stays within that toroidal core because it's round and the field doesn't emanate out as it would in a square transformer. What determines performance of the ferrite core? Different frequencies, the mix, the material with which it's made. And when you, like the end-fed antenna, when you use that core for that core that you use, ferrite core, we pick one that has the right mix of materials in it to serve at those frequencies. What causes a voltage to appear across the secondary winding of a transformer when an AC voltage source is connected across the primary? Just a transformer, put an AC signal in on one side, we get an AC signal out on the other side because we have mutual inductance coupling between the two. Of course, inductance has to do with coils. So mutual inductance is the best choice all the way around. You forgive me if I'm speeding up a little bit here. Voltage output of a transformer with a 500 turn primary, 1500 turn secondary. First of all, we would call that a 1-to-3 ratio transformer, meaning that if I put 100 volts in on the primary, then I would get I'd get 300 volts out on the secondary. Okay, so if I put 120 volts in on that, I'm going to get 3 times that out, which is 360 volts, as you can see in the little calculation there at the bottom. Now, what if we turn the transformer backward and we put the applied voltage on the secondary, or what is normally the output of a 4-to-1? Now it's going to work backwards. It's going to look like a 1-to-4. We put 1 in, we get 4 out. So the input voltage is going to be multiplied by 4 in this case. We're just using the transformer backward. Okay, this one is probably best just to memorize the answer because we have to go into the square roots and work the formula for that. And you can do that if you want to, but this is the explanation. Answer is 3.5 to 1. It's probably easiest just to memorize that. Basically, we do some multiplication, take a square root, and the square root of 12 is 3.46, I think, which is close enough to 3.5. And that's it. And with that, okay. Wow. Well, we're close anyway. Thank you, gang. It's been a pleasure. I'm going to go ahead and make the closing remarks here, and then I'll talk with you right after that. Again, this is Bob, K5CRX. We've been doing this general prep class for the McKinney Amateur Radio Club. This was session 2. Next week, we will tackle session 3, in which we will talk about receivers and a lot of the ins and outs, and that's good information in case you ever want to buy one, as a matter of fact. Nice to know. We'll see you the next time.